So with hashing methods, we can take virtually any amount of data and then we can produce some sort of hashed output. So that might be a fixed length value, or it could be a variable length. And you've probably seen sites like this. So this is Have I Been Pawned, and this is where the hashed values of passwords from data breaches have been cracked, and users can actually find out where their passwords have been breached. So the areas that we'll look at is the basic hashing types, and then on to the main methods that we typically use: MD5, SHA-1, SHA-256, and so on. Then to look at salting, that is to make the hash more secure. An important area is to understand when we have a collision, because obviously if we have a fixed length of hash, then it's possible for two different data inputs to produce the same hash. That's known as a collision. And then some of the Windows hashes, LM hash and NTLM hash, were historical hashes that we've used for Windows in the past. From there, we'll look at some benchmarks of hashing methods, and then on to message authentication codes, and we'll also look at key derivation functions here. In the last two topics, we'll look at one-time passwords, and then we'll have a look at Hashcat and how that actually operates. So before I start, I say that we'll focus mainly on cryptographic hashes. So those are secure hashing methods, but we can also have what are called non-cryptographic hashing methods, and these are used in hash tables, Bloom filters, and so on. But most of what we're going to look at is our secure hashes or cryptographic hashes. Okay, so how do we get some data? Doesn't matter what the data relates to. It might relate to a file, or it could be an image, or it could be the identity of Bob himself. How do we get a fingerprint for that data? Well, that was kind of solved by Ron Rivest with the popular MD5 hashing method, which took any amount of data, virtually, and then was able to create a fixed length MD5 hash. It just happened to be 128 bits long, and unfortunately that isn't long enough for our current standards. So with MD5 we create fixed length. Either we can represent that with hexadecimal, so as it's 128 bits long, then we have 32 characters, or 16 bytes. Okay, 32 hex characters there, so you can count them there. There should be 32 there, and those represent 16 bytes of our hash. If we change one character, we can see we get a completely different hash there. And we can take any amount of data here. The other way we represent it is with base64 format, and in this case we get a smaller, slightly smaller hashed value for our base64. So that was 128 bit, and really isn't long enough for current modern standards. So an improvement on this is SHA-1, and SHA-1 has 160 bits as a hash, and if you think of that, that's 20 bytes or 40 hex characters here. This is giving us a longer hash, so there's less opportunity to create a collision in there, because there is an increased number of hash values there. Okay, so again, we can represent in hexadecimal, or we can represent in base64. Unfortunately, Google found that it was possible to create a hash collision with SHA-1. It took them many months to do that, and a lot of computing power, but it compromised the SHA-1 hash. So we typically don't use SHA-1 these days because it's too short. Okay, so we can change one word in our input, and we can see here we get a completely different value. Hopefully all of the bits will change on the hash output in some sort of random manner that's not predictable. Okay, so here's an example. We can use OpenSSL MD5 to create our hash value, and we can also use MD5 sum from there. Where we typically use it is to be able to fingerprint our files. So we might take a hash value of each of the files that we have, and so if anything changes in these files, we compare it with the original hash just to make sure it has some credibility. We also see it in what's called digital signatures. With this, we take a hash of the data and then we will sign it with our private key to show that we've validated the data. So we see here on this certificate, there is an MD5, a SHA-1 hash has been taken off the data in the certificate, and then a signature is taken from that hash value. Okay, so here's an example here of when we use it, hashing it for storing passwords. So Windows at one time used the MD4 hash, and that was before MD5, and where we can take our value and then hash it from there. We also see it within Cisco configuration. We can see here 5 means that it's MD5 encoded. The one here identifies that hash value. The salt is included, as we'll find, quite a small salt, and then there is the hash value there. So this is a way to store the password in a hashed form. With hashing methods, we shouldn't really be able to mathematically go back in the reverse way. We should only able to go one way. But unfortunately, it's fairly easy on some systems to do the reverse back from the hash to the original data. And one way this can be done is with our rainbow table. And with our rainbow table, we can actually create a whole lot of hash values that relate to our data. And then we just basically go down to find the hash, and we should be able to find the mapping that leads back to our data. The other way is that it's possible for us to attack with a dictionary. And with a dictionary, we could create the hash values for all the most common words that are possible, and look at permutations of these, add a 1 and a 2 to the end, make it uppercase at the start, and so on. In this case, it makes it easy for us to be able to search through the pre-hashed values and find the one that matches, and then from there it should be possible for us to discover what the original value was. So in order, then brute force would support us going through all of the different permutations, say from A up to ZZZZ. That's a brute force. That's going to take probably a long time to compute. A dictionary attack will take common words and then try to put them together to see if they can find the hash. But brute force is the fallback that we would have for our hashing methods. And the problem that we can have, as we've seen from IBM Pond, is that let's say that a hash value has been compromised, then it's possible for someone to create a jump-off point to try different accounts with the same password. So it's very important that you change your password regularly, just in case it's been breached. So this is one example here, and it happened quite a while ago, but it just shows you how sloppy users can be. There was an Adobe hack with 150 million accounts compromised, and the top password was 123456, and it occurred nearly 2 million times. Unfortunately, there was not even a salt value used for the attack, so every single hash was cracked for that plain text password. Okay, so let's try and understand how long it will take to crack our hashed value. So if we have a 7-digit password or 7-letter password from A to Z, then how many passwords are possible? Well, in this case, it'll be 26 to the power of 7. And then if we crack for 100 billion per second, then we're going to divide by 100 times 10 to the 9 here. So we'll just give that a try. So let me bring this up. Okay, so we'll open up our Python here. So we have got the number of passwords is going to be 26 to the power of 7. And then the time it's going to take us to crack these, if we do 100 billion, will be the passwords divided by 100 times 10 to the 9. Okay, so we'll print that out. We'll see. So you can see it takes us 0.08 seconds to crack every single 7-character password which has been hashed. If we can crack it at 10 billion per second. So now let's try for upper and lower case. So this time we need 52, and we'll just compute. And it's a bit better, so it's 10 seconds to do the whole of all of the hash values. So we'd be able to go through every single password from all A's in lowercase to all uppercase Z's. And if you're interested, the number of passwords that are possible for that is this number here. So now let's try for 62. And we'll print that out. So that's the number of passwords. So let's see how long it'll take from there. We'll just print it out. You can see there that takes 35 seconds. Okay, so this is the ultimate, this is the fallback for brute force. This is the total amount of time it's going to take us. So we would often be looking at maybe a 10-character password. So you can see that for that we have many more passwords, and let's see how long that will take us. And you can see that takes us much more if we want that in terms of minutes, hours, and days. Okay, so it would take us 97 days to be able to crack all of the passwords for a 10-character from little a to big Z, and also for the characters there. Okay, but that is the maximum space for all the passwords, and most people won't pick all of the possibilities, so we typically decimate our space for that. Okay, so let's look at some of the methods that we would use for our hashing techniques. These are some here. LM hash has been used in Windows, not very good. SHA-1 was 160-bit. SHA-2, also known as SHA-256 for a 256-bit version, was a new method to implement the hashing methods, to implement our hashing methods. But then NIST defined that they wanted a new method that was lightweight and fast, and they came up with the SHA-3 standard, which was based on KitKat. And this method uses, if you're interested, a sponge method to be able to store the state that the data is in, because we take data and then we crunch it, and then that is defined in various states that we have when we are adding the data. So this method created the SHA-3 standard, and it's often used in Ethereum, as we'll find out later in the module. There are some methods that are quite slow in their operation, and bcrypt is one of those. As we'll find, PBKDFS2 is another slow method, and I'll explain those in a little minute. And there are non-cryptographic methods that are very, very fast, and they're used in hash tables and Bloom filters and so on. Murmur and FMV are two examples of these. So here we are. So 128-bit. There is a collision highly likely. I'll explain what collisions are in a little minute, but you can't really trust the MD5 signature to be mapped to one instance of the data. We can prove that with 160-bit, but again, there might be the possibility of a collision. So these days, we typically focus on 256 or 5112-bit hashes. SHA-2 is available in SHA-256 or 512, but now Blake is also a very popular method for a modern standard. And SHA-3 is possible. But sometimes we want to create a variable output. We might have a key that we want to create, or a fixed length hash for 200 bytes or something like that. For that, we use an XOF function, and we can actually define the size of the output for the hash. Rather than the fixed outputs that we have here, we can define a variable output. So Blake2XS, Shake are two methods that we can actually use to be able to create that variable hash output. And this is an example here. This is TrueCrypt. TrueCrypt has a key which is generated that opens up the header of the disk. The header of the disk, and it contains all the master keys that have been used for the encryption, all of the encryption methods and so on. To protect that, we use what's called PBKDFS2 or password-based key derivation function, and what's used in Wi-Fi and so on. And for this, the user would put in a password. There will be a stored salt value. When these two are added together, they will generate a key. The key is then used to open the box. The box has the encryption keys, which are used to access our encrypted disk, as in TrueCrypt. The advantage with this is that it's very, very slow. And the reason it's slow is that it does a number of rounds that it goes through. So the rounds means that it's got to do it sequentially, so that it will stop a GPU from actually paralysing the operation. Okay, so let's look at salting and why that's so important. So with salt, what we have is that we add maybe a string onto our data, our input data, and then we can hash that. So in this case, we'll add the string Bob to the start or in the end. It doesn't really matter as long as we know where it's going. And then that will produce a different hash value. And then for each salt value, we will produce a different output. This makes it extremely difficult for somebody to pre-compute a rainbow table now, because there would be an almost, well, not infinite, but there would be a massive amounts of data that would have to be stored to store every string and every salt value. Okay, so when we store our passwords, we need to store the salt. If we lose the salt, then we're going to be struggling to be able to regenerate the password again. So in this case, we have a salt value here, Fred, and we have a password of a password. And then when we take salt and password, we generate a hash value such as this one. The one here identifies that this is MD MD5 method. So the format that we typically have is the dollars will differentiate the fields for the hash value, the salt value, and then the cipher. We can also get another field for the number of rounds that it does, but in this case it's fairly simple. And here is a password stored here. There is the method, there is the salt, and there is the hash value. When the user logs in, the system will take the salt, the user's password, and try them to get the cipher and checks that against the cipher that's in the storage. So here's an example here. So we're taking a salt value of this and a password of this. We can see that there's the salt value and there is the hash value. So when we take the user's password, which is red hat here, add it to the salt, then we should get the same hash value back again, and the user should be able to log in. So a very important understanding about the security of our hashed values is collisions. And a collision happens when we take different data and it produces the same hashed output. This is known as a collision attack. So the worst thing is that if we have a similar context or a full context, it means that someone can change a message to have a different meaning and produce the same hash value. So for example, we might take putty as a program and we might show a hash value. Someone could put a backdoor into the software and add some other data to produce the same hash value. So when someone downloads putty, if they don't know, they could check the hash value and it may look okay. So it's very important that we avoid any collisions which could compromise the trustworthiness of our system. It can also happen in some methods. If they've not been designed correctly, we can force a collision. This is an example here. By flipping a few bits in the input data, it's possible to create a collision. But these days, the methods that we have for SHA-1, SHA-256 are typically fairly secure, and they've been designed not to avoid this type of problem. And it happened with Nat McHugh, who took two images, one of James Brown and the other of Barry White, and used a birthday attack on these images. By stuffing bytes in, it is possible to create a collision in a reasonable amount of time. For MD5, he used Hashcat, as we'll cover later, using the CUDA architecture, and he found that he could produce the same hash value for the images, and it only cost him 10 cents on the Amazon GPU cloud. And I think these are I instances that we would use, and they have GPUs fitted, integrated into them. They're very expensive to use, but the computing power is massive. And I think he even managed to do it with 3 images with MD5. SHA-1 is a lot more difficult, and SHA-256 is almost impossible these days. Okay, so at one time we used LM and we use LM and NTLM hashes with Windows for older systems. And if you don't know, then what we have is every computer in a Windows domain or workgroup has a unique identifier, and the identifier here identifies the domain that you connect to, either in a workgroup or on a Windows domain, and then the user at the end will actually define a unique number. 500 is the admin, and users start on 1000 and go up. This is known as the SID. In a Windows domain, then the Windows domain controller controls all the computers in the domain. But on a standalone machine, the passwords are stored inside the SAM hive. This is a file on the system, and it's obviously protected when it's running. This is the example of the SAM here. And if we do a cold boot, then it's possible to have a look at the SAM here. So in this case, by cold boot, we could take the disk out and we could actually have a look in the Windows System 32 config into the SAM hive, and then from there we can use tools of pkhive and samdump2 to be able to export the passwords hashes from there. And in this case, John the Ripper is used to be able to search for given passwords. lmdes is the hash type that's been used here. You can also use offcrack, and that's a method for loading up rainbow tables. But these days, typically we can't use rainbow tables because most hash passwords are salted. So we can also, rather than using the cloud, we can actually purchase GPU hardware. So this one here is 1.5 tera hashes. So that's times 10 to the 9 is giga, times 10 to the 12 is tera. So you can see that does 1,000 giga hashes per second and costs between $3,000 and $5,000. But it will also cost quite a bit of money for the electricity supply for it, and it'll be very noisy too. This one here is a 25 GPU hash cracker, and it can crack an 8-character NTLM password in 5.5 hours. But it's possible to get even larger ones than this, and we can get large arrays of computers. So this shows a very basic table for our different hashing methods. So these are fast hashing methods. So it's fairly quick to crack. So in this case, if we go up to 9-character length, then NTLM can be cracked within hours. We keep going up here. These are all the fast ones, but they're getting slower here. You can actually see we're starting to move to make it more difficult, and now it's becoming quite difficult to crack an 8 and 9-character password for these Kerberos and MD5 crypt. There's LastPass and so on. And as we keep going, this is a popular one here too. So you can see here we're pretty well protected up to about here now. So we have 9 characters for a PBKDFS2 SHA-512. It's going to take us it's going to take us many years to be able to crack that with brute force. But if we keep going up, we can see that Bitcoin, actually, even if you have an 8-character Bitcoin password, it can take 59 years to be able to crack it. So these are defined as the very slow methods. And the reason for that is that they have rounds that they go round, and we will hash for many times, and that will defeat the GPUs. We can also have other ones which break the GPU, such as Argon 2 and so on. These are the slower methods here, and these are the fast methods. So we would typically not use the fast methods for hashing a password. We're probably not going to be using these ones too if we can avoid them. If possible, we're going to be in this region in here to use these passwords, the 7-zip and so on, for really secure ones there. So you can see that even for an 8-character, for a 6-character Bitcoin, it can take over 2 days to crack them. Okay, so let's look at how fast these methods actually are. So here we go. This is a sample benchmark that I've run here, and we can see here the non-cryptographic one is the fastest by far, Murmur. But if we need a cryptographic hash method, we would use these ones here. So SHA-1, SHA-256, SHA-3, and so on are all fast. SHA-1 slightly faster than MD5 and faster than SHA-3. But then the medium speeds take us into MySQL and LDAP SHA-1 password. The slow ones take us into PBKDFS2, which is used in Wi-Fi, PIX, Cisco PIX, and so on. And then the ultra slow ones are the LM hash, APR1, which is used in Linux, bcrypt, DES, and Oracle 10. And they kind of vary with their format. Hashcat will have a good guess at what method that we're actually using. But if we see sometimes, then we'll see the rounds. In this case, 2A identifies we're using bcrypt. 05 identifies the hashing method. 05 identifies the number of rounds that we actually go round. And then in some cases, we'll see the salt value, and there's the method, and then there's the hash value there. Okay, but they all differ, and hopefully we'll be able to identify which type that we're using and to be able to parse it properly. I could probably run a quick benchmark here just to see them. So this is, we're just benchmarking this string here, and hopefully you can see there's all the hashes there. Remember, we've got to store the salt there, and you can see this one looks to be the fastest, and then the slowest is this DES, and bcrypt and APR1 are slow. Oracle 10 is also slow there. So we're only getting 126 hashes per second for Oracle 10, where for SHA-1 we get nearly 500,000 hashes per second that we can actually try. Okay, and I've just set it up that bcrypt does 5 rounds because I want to speed up here, but typically we would have many more than 5 rounds to slow it down. But to make sure that this would run quickly, then I've actually set it up with only 5 rounds. Okay, so one method that's super fast. So Blake was one of the contenders for SHA-3, but CAC won. So that is now the standard for SHA-3. But Blake has developed, and the Blake 3 method is the fastest cryptographic hashing method around. We can see here, this is 1.28 gigabytes per second hash rate, and we've got to go all the way down here for MD5. So we can see here between MD5 we have virtually times 4 times faster. If we keep going down, we've got SHA-1 there, and here is SHA-2 there, and there's SHA-3. So SHA-3 is doing 100 megabytes per second, as opposed to 12 or 13 times that speed for Blake 3. So it's been applied a lot these days into very fast hashing methods, and is obviously very useful when we need speed for our hashing method. So this should hopefully be a little test for this. Just taking a minute to run. So these are some of the cryptographic hashing methods, and we'll just have a look to see if we can find Blake 3 hash. Okay, so there's with Blake 3. And there should be some Python code there. When it comes to slowing down, then we obviously need to be down here. And the reason that, as I said, we do this is that we have a sequential hash. So we'll take a SHA-256 hash, and then we'll feed it in again, and then take a hash of that, and we'll keep going round. The advantage with that is that we might have an array of processors, such as in a GPU, and it's not going to be possible for us to be able to parallelize the method because only one of the processors can hash at a single time, takes that hash, and then we'll hash it again. So it will disable all of the cores that we have in our GPU apart from maybe one. So this is an example here. This is Splunk that uses this method here. And we'll take a password and a salt. And we can see 06 relates to the method that we're using for this, which is SHA-512 crypt. Okay, so this is my password here, and password required 2123 and a salt value here, and then you can see it produces this here. So we should be able to see the salt value in there. So the salt value is here. So between the $2 values, we can see the salt, and then there is the hashed value. If we now use Hashcat, and Hashcat needs a number at the end to be able to identify which hashing method, then it tells us how quickly it can hash. In this case, it's only hashing at 454 words per second. So you imagine if you had a big dictionary of words, it's going to take you a long time to go through that. If it was hashed with MD5, we can hash with the same processor. This is a 2.6 gig i7 processor at 17.33 million words per second. So you can see the big difference between using SHA-512 crypt and MD5 in terms of the hashing. So we'll just have a quick look at this one if we can. And then we have the non-cryptographic ones, and these are super fast, but they're not actually very secure. So if we're looking for a really fast method, we can pick Spooky or City Hash or XX hash. Meow hash is a very fast one. This one here is not really very useful at all, but it's extremely fast. CRC32 we use on disks and for integrity. Google recommend that we use these hashes because they give good they are free of major problems. XX3, Spooky, or Mum hash, and so on are some of the strong non-cryptographic hashes, and these are here. So here's a few there if you want to have a look, but we can pick off Spooky hash and XX hash and so on. So these will give us ultra fast speeds compared with our normal cryptographic hashing. So I don't know if we can see a more traditional hash appearing. Let's see if we can find Blake. So there's Blake here, and you can see it's running at that speed, but if we look at the fastest, it's running at least 10 or 20 times faster than our cryptographic hashing method. Okay, so another area that we use hashing methods is within our message authentication codes. So with this, here is our normal hash. We take a MD5 and we'll add in some salt and we'll create our hash value. Within an HMAC, what we do is that we take a symmetric key, a secret key on either side, and we sign that hash. So as long as Bob and Alice have the same key, then, or the same secret, then they will take the hash, and using the key they will produce what's called an HMAC signature. This allows us to be able to check that the data is the same, hasn't changed, and also that the correct secret key has actually been used on either side. And it avoids when we have Eve intercepting a conversation, because Eve won't be able to sign any of the messages because she doesn't have the secret key that Bob and Alice negotiated at the start. Another area that we use hashing methods is to generate encryption keys. And we do that by taking some secret or some random value, feeding it into a key derivation function, and then producing an output encryption key. So here's an example here of HMAC key derivation function, or HKDFS. This is used in TLS 1.3 and is an extremely useful method for generating encryption keys. With this, we take a secret, it could be a password, or it could be some random value or a seed value that they negotiate, such as through Diffie-Hellman method, and we take a salt value, and both Bob and Alice know the secret and the salt value. They put it into the key derivation function. In this case, we take a SHA-256 hash and feed it in with the secret and the salt, and that will produce an encryption key for us, say of 256 bits length, that we can use to encrypt. Alice, on the other hand, uses the key derivation function with the secret and the salt, and she'll be able to generate the encryption key, which can then decrypt the data that is sent. So here we go here. This is an example here with some salt and using a password, and the salt will produce this key, and then this key can then be used to be able to create the key that we're going to use for our encryption, perhaps 128 bits or 256 bits. We can, or even 512, we can take part of the output that we want. Just let me find the key derivation function. And I'll find my H key derivation function. Here we go. And we'll try this one here. Okay, so we define the hashing method, and we define the length of the key that we want. So for 16 bytes, that's 128-bit. For 256-bit keys, we'd go for 32 bytes, and then for 512, we'd go for 64 bytes there. So we can take our passphrase and our salt value. Remember, the salt value needs to be stored and given to Alice. So with that, and with a certain size of key that we need to generate, and for a hashing method, then this is the key that we actually generate. So this is the safest way to create encryption keys with this, and it's protected against a number of attacks that we can have on the keys. We can also use one-time passwords, and they're useful because what we can do is we can take our data and then we can hash and hash and hash and hash again. So that would create a whole lot of hashes. And let's say we had to identify this hash here, and only by knowing the original seed of the hash would we be able to produce this hash. We could then produce the previous hash and so on. So in this way, it is possible for us to be able to continually hash the values, and only if we know the original seed, which might be our password, can we generate any of the other hashes. We can also have it on a counter. So with a certain value, we can produce a certain hash value that's been hashed so many times. And we use this, of course, when we use multi-factor authentication. We're logging into a website on our mobile device, then we'll get a one-time password generated. That can be a timed password, so that the password only exists for a certain amount of time, and if we take too long, we need to regenerate a new one. So now let's look at the practical implementation. So in the lab, you'll be able to implement with Hashcat, but we'll look at some of the core principles around Hashcat. This is my Hashcat here, and it's a very powerful tool and will often decimate our hashed password spaces. The way it works is with three main methods. The fastest tends to be rule-based. There's a rule that is applied onto the password, such as bringing words together and so on. A dictionary attack goes through common words in a dictionary, one at a time, and then trying each one of them. And then if those don't work, we can go for a brute force attack, which will go from all A's up to all Z's and so on, and take all the permutations in between. And there's a number of attack modes within there that I'll explain too. So the options that we have is we define the -m as the hashing method that we want. So a hash method of 0 relates to MD5. There is an attack mode that I'll explain in a little minute. We can run a benchmark to see how many hashes we're going to get for the processor that we have, and a number of other things that we can actually define, such as adding a rule file and so on. And then if we want an output, we can just output it to any file that we want with the -O option. The -A option allows us to create the method that we're going to use for our attacks, such as we're going to use brute force, or we're going to use permutations and so on. So within our -m option, we have different ways that we can hash. So in this case, we're putting the password and the salt, and the dot there means the concatenation of strings. So if I have Fred and a salt of ABC, it will create a string of Fred ABC, but in this one here, I can have the salt first and then the password after it. Okay, so we select the ones there, SHA-1, and then we go down to SHA-4 here, NTLM, there's SHA-256, there's script, very slow password there, and so on from there. Okay, so we can pick off what we think is the right way that the hashing has been done, what the right hash method is. And then we can look at the basic output format that we want to store that as with this output format here. So here's an example here with Hashcat. So we're hashing 1400, which I don't know if we can actually see from here, is SHA-256. So these are SHA-256 hashes there for that, and you can see that it's managed to find the mapping here as the word help. So for this, we're looking at a dictionary attack. And here is the dictionary here. So within the dictionary, there'll be the word help. So this isn't doing brute force, it's basically going through all of the words in the dictionary until it actually finds the right one, and then it's able to solve it. In this case, it's solved it very, very quickly. And so in this case, we've got an identifier of 100, which is SHA-1 or 160-bit hash. You can see it's a shorter hash there, and it's managed to do it again. And we can see here there's the words file there, and within the words file we've actually got the word help, so it would have found it. Often we have a words file with the most popular words at the top, so that we'll hit them first and the least popular near the bottom. Okay, we can also have what's called a combinational attack, minus A1, and with this one it'll take two dictionaries. So you just remember that you use jam or jar or something like that as the first word, and then you've got a second word of car or cat or cow. I just can't remember. So with the minus A, we can take our two dictionaries together. So we've got jam and car, and jar and car, and so on. So this can be useful if you actually know that there's 2 or 3 words that have came together to be able to create the password. But as a fallback, we can go for our brute force, and with brute force we end up with character types. So the percent U identifies uppercase, the question mark, sorry, the uppercase U, and then the small l is for lowercase. Numeric values is a question D, and so on. So with this, we can actually define the character sets that we want for our passwords, and we can define that we want an uppercase first and then all lowercase values there. So we can feed in our possible character sets, and then it might find certain passwords. So for this, we might say uppercase, and then we want say 7 lowercase, and then a numeric value at the end. So this would find passwords which started with an uppercase, had lower cases, and then had a numeric value, and it will try the values from 0 to 9 here at the end, and it will try the values from A to Z here, and it will try the values from A to Z in lowercase here, and so on. It will go through all of the permutations. Okay, so here are 2 examples here. So in this case, we have our character sets and go through our permutations. So if it was all lowercase, then we go from all A's to all Z's in this case. Okay, so here's an example here. 1, 2, 3, 4, 5, 6, 7 characters there. 1, 2, 3, 4, 5, 6, 7, 8. I think there's 8 there. So it's going to go through up to 8 character lowercase and try each of the permutations. So you can see what it does is it will start with A to A. It will then go on to A to Z, A to ZZ, and there are 26 of those, and there are 676 from AA to ZZ. If we now go from AAA to ZZZ, there are 17,576 in there, and then it's gone up to the next one, and this is for our four character AAA to ZZZ. But what it does is when it finds one, then it will stop. So in this case, it only had to go through nearly 60% of the permutations to be able to find what the word was, and in this case you can see the word is help. Okay, so it will go through each of the sizes for all the permutations, in this case for lowercase, until it finds the match, and then it can stop from there. Okay, so there's an example here. We might know that our password is HEL, and there's another letter here, and we know it's lowercase. So in this case, we can actually define HEL question mark L. So you can see it's going through each of the permutations again. And in this case, we can see that it only has to go through 26 different letters here, because it's taken HEL and then going through A, B, C, D, and so on, and it gets up to P, and it manages to finish. P is the 16th letter that it actually tries. Okay, so if we roughly know what the password is, we can reduce the key space down greatly. Okay, so we know that it's a 3-character starting with HEL, and it's a numeric value at the end. So in this case, I've used HEL with a 9, and we can see here that the actual key space is only 10 long, because there are only 10 numeric values. So we're specifying the percent %D there to identify that this is a numeric value there. Okay, so there's the attack mode there, and this is SHA-1 that we're dealing with here, 160-bit. And then we can have rules, and this is where it gets really interesting. So the rules will go for standard ways that we can input things. First one is a password list. So in this case, we can use the -L. There are fairly standard lists of passwords that can be fed in. In this case, there are 14,000, more than 14,000 passwords in the raw queue, and we can use that as our dictionary to be able to identify hash values. So in this case, we're using MD5, and we can see here that the number of words in there is that number, and the one I've selected there, and it's managed to find it from there with 1, 2, 3, 4, 5, 6, 7, 8, 9 as the hash for that one, and it found it very quickly. It was the 4th word that it tried. Then for the rules, we can substitute various things. Like for example, we can use rules on capitalize. So we can capitalize the first letter, lowercase the rest. We can append a certain character onto the end, and so on. And these can be added. And there are standard rules that we can actually apply from in there. Okay, so a common rule that we have is to change an A for an at, an L for a 1, 5 for an S, and so on. And again, this is one of the standard rule sets that we can actually have to be able to implement that. Okay, and this is an example here of using the battlefield hash data set, which came from a game. And this is with the raw queue list of passwords. We can see here are the resolution of those related to the hash values. Okay, so that's been an overview of hashing methods. Hopefully you understand now the range of hashing methods, the importance of salt, collisions, how fast they are really matters, how we can use message authentication codes to be able to create a keyed, it's called keyed hashing. Also how we can generate securely a key, an encryption key from our hashing methods using HKey DFS, our key derivation function, how one-time passwords can be used, and then how Hashcat can effectively target itself on cracking hash values. Okay, thank you.